So, as I mentioned, the topic of the webinar is troubleshooting your OpenSPR experiment, part 3. We are basically going to look at the Streptavidin, Liposome, and then the hydrophobic sensors. We are going to look briefly at the chemistries on the sensor surface, how to successfully immobilize a ligand on the sensor surface, and then how to troubleshoot for other artifacts, just like non-specific binding and other things, as we have done for all the other 2 sensors that we have looked so far. So, like I mentioned, Nicoya has a variety of sensors, and the sensors are grouped according to the coupling procedure. Like we have covalent coupling, under which we have our plain gold sensor, the carboxyl sensor, and then the amine sensor. We like to refer to these two as the fraternal twins because they basically employ very similar chemistry or the same chemistry. On the far right is the the capture coupling, under which we have the NTA that we talked about last webinar, and the biotin and the Streptavidin sensor. On the bottom is the hydrophobic coupling technique, where we have 2 types of sensors, the liposome, which we call the LIP1 sensor, and then our hydrophobic sensors. So let's revisit a little bit our previous webinar, just to give us a good transition into today's talk. So previously we discussed the carboxyl sensor. We discussed that there are these COO minus which are going to be activated and then coupled to a primary amine from an incoming ligand. And we mentioned that you have to put your ligand in a buffer that is going to let the ligand be positively charged, because you are going to have it to interact with the COO minus on the sensor surface. We also talk about how to reduce NSB on these sensors by using things like high ionic strength, pH, and blocking molecules. And then the subsequent webinar was on the NTA sensor, and most of the focus was on this coordination complex. We talk about nickel being the boss in the room where we need to protect it, because if it's chelated away by, let's say, EDTA, there's going to be no coordination complex. And we also looked at things that would also compete with this histidine coordination site, like if you have excess imidazole in solution. We also mentioned that the nitrogen here on the histidine has to have the lone pair of electrons, and these will happen in basic to slightly basic pH. So you wouldn't want this reaction, it will not occur at acidic pH. What about today? Today we are looking at the Streptavidin sensor. We are going to look at it in terms of the sensor, the chemistry on the surface of the sensor, which is biotin molecule, and how we can bring in Streptavidin, which is going to actually interact with our incoming biotin-related ligand molecule to form something like this on the surface of the sensor. After we look at that and look at how to be successful on this sensor surface, we move on to the liposome sensor or the LIP1 sensor. Our liposome sensors would have lipophilic chains on the surface, which will be used to immobilize things like intact liposomes, vesicle, or nanodiscs on the surface, as we see here. On the other hand, this is the versatile hydrophobic sensor that would form a monolayer on the surface of the sensor with your hydrophobic ligand molecule. So that brings me straight to the outline of today's talk. Today, like I mentioned, we are going to review these sensor surfaces, the Streptavidin, the LIP1 sensor or the liposome sensor, and the hydrophobic sensor. After we have identified or we have refreshed our minds about the chemistries that exist on the surface of these sensors, we are going to look at how we'll be able to stabilize our ligand on the surface, just like we did with the carboxyl and then the NTA sensors. After we successfully immobilize our ligand on the surface, we also look at how we could optimize the binding kinetics, how we could get our KD, our Ka, all the parameters that we want without any hassle by using things like buffer consideration, sample handling, and storage. Today I'm going to bring in another thing, which is going to be temperature, because We know that streptavidin is a very robust and stable protein, but then I'm going to talk a little bit about how to handle it when you are doing SPR, especially for our system which uses a very sensitive detector, unlike other solution-based technique whereby you could store the streptavidin at, say, room temperature for some time in solution and it will still be fine. But then we'll find out. I'm going to show you like real data that would tell you that we have to control the temperature when we are handling with these things. And the third item that I'm going to talk about is how to troubleshoot your data. Just like I do for all the other talks, we are going to look at bulk shift, non-specific binding, and air spikes. Today, we are not going to dwell so much on this because we have talked about them extensively, and they can be implied, like they can be cut across different chemistries. So the NSV, how to control NSV in, let's say, carboxyl, could be similar ways to control NSV in streptavidin, or let's say in lipid sensors. The one thing I'm going to introduce, which is new in this artifact category, is the mass transfer effect. And I'm not going to talk about it so much. I'm going to leave it. And then when we get to that particular slide, then I'll talk about it, because I always mention to use moderate amount of ligand, and if you use too much, you could run into mass transfer effect as well. So we will get to know it pretty soon. So sorry about that. So on the strength, let's come straight to the streptavidin sensor. On the sensor surface, as I mentioned, we have biotin groups that would require coupling to streptavidin, as we see here, which is a tetrameric protein. And then the streptavidin on the surface will be used to immobilize an incoming biotin-related ligand, as we see. Then the ligand would be used to interact with our incoming analytes. Then we will get our kinetic parameters that we want from this interaction. So we saw in the past that on the carboxyl, you would need to activate the surface with EDC NHS before you bring in your ligand, and then there's going to be a blocking step. Also, in the NTA sensor, we found that you need a nickel and all those other things. But here is a simple, straightforward chemistry where you buy your sensor chip, you clean it a little bit, and then you put on a streptavidin, and then your biotin-related molecule comes in. So why is it important to use the streptavidin sensor? The streptavidin sensor uses, as we already know, it uses the biotin streptavidin interaction, which is one of the most strongest non-covalent interaction known, with a very, very low KD, dissociation constant. And then, so what advantage do we get in SPR is that the ligand, when it's bound to the surface, it doesn't bleed. Remember, in the last webinar, we talked about ligand bleeding, whereby during your reaction at a point after several analyte injections, you may need, on the NTA sensor, you may need to re-immobilize more ligand. But here we don't have that situation. It's very similar to the carboxyl coupling, where when things, the ligand gets immobilized on the surface, it's kind of like glued to the surface. So that's another advantage. Because the biotin streptavidin interaction is very rapid, you may need very low concentration of the ligand during this. So it's another advantage. And then literature has it. And then we also know after several uses of these sensors, and some of our customers also could testify that these reactions are stable, or they would occur at a wide range of pHs. We saw on the NTA sensor that you may need to do the ligand immobilization at slightly basic pH. But here, you may get by with a little bit variation in pHs. The second group that I'm talking about is the ability for the sensor to be very versatile. The streptavidin molecule could be used to capture drug molecule as long as they are biotin-related, sugar, nucleotide, proteins, and even other small ligand or peptide. All what you need is a biotin group. And this biotin group, if you don't happen to have the molecule already biotin-related from a commercial vendor, you can do it yourself by using either a chemical approach and then enzymatic approach. Look here that I've only put the NHS ester. Doesn't mean that that's the only one you could use. You could use different kind of chemical modification. and then you can get your biotin attached to the ligand of interest. The choice, again, they both have their pros and cons, but then when you do an enzymatic modification, a biotinylation with a biotin ligase, of course, it's going to be specific, just like every other enzymatic reaction. You would have better orientation compared to the chemical modification. And the last thing here is that the biotin molecule, being that small, like a 300 Dalton molecule, is not going to interfere with the interaction on the sensor surface. So knowing all these advantages that comes with this sensor chemistry, let's talk about how we could be successful on the sensors. So, sorry, I was getting ahead of myself. An example is the sensor, the advantage is that you could use the sensors in a Streptavidin sandwich sensor assay. We mentioned that in the previous webinar, we compared carboxyl sensor to NTA, and we saw a similar pattern. On the NTA sensor, the ligands were uniformly arranged. Similarly, on the Streptavidin sensor, the ligand will be uniformly arranged. Unlike what we see here in the carboxyl, because it relies on a primary amine that is exposed, you could have different orientation of your ligand on the surface. As we see here, maybe this ligand may not be, the ligand binding site is not going to be available for an analyte to interact with. So would this one be? So you have more efficiency here compared to there. This, though, does not mean that the carboxyl sensor is not a good sensor. We are going to talk about how you could incorporate this carboxyl sensor into the Streptavidin chemistry pretty soon. That brings me to my next slide called the Strep Sandwich. If you have a carboxyl sensor and then you run into orientation issues, like you know that your ligand is on the surface because you get that response, but then when you put the analyte on the surface, you don't see good interaction, and you have done all the good things, you have optimized your buffer, everything has to work. It could be that you are running into orientation issue, as I showed on the previous slide. So what you could do is that you will use a Strep Sandwich. The Strep Sandwich is that because the Streptavidin molecule, that maybe you would have a Streptavidin in your fridge or in your lab somewhere, the Streptavidin has primary amine because it's a protein, of course. You could couple it to the carboxyl sensor surface as shown in the diagram here. And if you have your ligand biotinylated, or you could decide to biotinylate it as we have shown previously by chemical biotinylation or enzymatic biotinylation, you could still have this. So basically you have converted a carboxyl sensor into a Streptavidin sensor, and your analyte doesn't have to have any tag. It just have to be able to recognize this binding site. So we find out that the Streptavidin molecule itself could be very versatile, and also here the carboxyl sensor, it has a disadvantage, but the disadvantage could be used in a combination that it could be overcome by using it in a combination with the Streptavidin to immobilize biotinylated molecule. An example is shown here. For example, in our lab, we decided to show how this is possible by first immobilizing different concentration of Streptavidin, like 50 microgram per mil or 200 microgram per mil, on a carboxyl sensor. Notice that we are working at slightly acidic pH because we want Streptavidin to be positively charged, to be able to couple to the COO groups on the sensor surface or on the sensor surface. And then we also try to just add, say, surfactant, which is in the blue curve, to see how it changes. We found that we see up to 2,000 RUs when you use 200 microgram per mil Streptavidin. And the twin, 0.1% twin doesn't really change so much. So here, yes, you could do the Streptavidin sandwich on the carboxyl sensor. Now that if you have the Streptavidin on the sensor, you could now immobilize your ligand, which in this case, we use a biotin HRP ligand. And again, you will see that if you took the black curve and then you immobilize the ligand, you get about 200 RUs to work with. And then you get the other ones as well. But here we see that in the presence of the one that used the buffer had the twin in, there was more increase in RU. But overall, I would say that yes, from here we can say that yes, you could overcome the orientation issue on the carboxyl sensor by using this approach. So I was talking about streptavidin and it being very robust, and the fact that we should handle it with care. And some may ask why, because streptavidin is known to be stable protein. Literature has reported up to 70 degrees and it's still going to be stable because the subunit, the 4 subunit, did not dissociate in some of the work that I've read. But why do we care about it so much in SPR? Remember that in SPR, our system, Nicoya's system, has very sensitive detectors. And then the streptavidin molecule is going to be localized on a solid support. The gold is on a glass slide. Unlike the solution base, which may not be as sensitive to precipitation as our system that we have. So we encourage our users to always try to handle the streptavidin at low temperatures. Like for instance, in this situation, if you have a streptavidin that has been sitting at room temperature in a buffer, and then it's injected onto a biotin sensor versus the streptavidin that was freshly thawed from the freezer, we find out that the intensity of the one at 50, the intensity of the signal reduced by 50%. So, and also remember that you are going to take this streptavidin surface and then put in your biotin-lated ligand. The amount of streptavidin on the surface is going to detect how much ligand you can immobilize. So if you have your intensity this much reduced, it means that your signal is going to reduce as well by 50% in your subsequent sensorgrams. So you handle the streptavidin with care. And then I show you that, yes, indeed, what I'm saying, when you have a streptavidin that has been sitting at minus 20 and was freshly thawed and was used to immobilize biotin-lated protein A onto the sensor surface, and the protein A was interacted with IgG, we find out that there is very low NSP, which is what we want, because NSP, nobody wants to deal with non-specific binding in biomolecular assay. We did a similar experiment at 4 degrees when the streptavidin and the other reagent were sitting in the fridge, and again, very low NSP. But then when you have it at room temperature, we see that there is very high NSP. And this is not good, because you see that even to the end of the run, there is so much drift that it's not even stabilizing. So there's going to be more NSP. So make sure that the streptavidin molecule that you use for your experiment, if it's in solution, you keep it in the fridge. At least if you don't have a minus 20 freezer, keep it in the fridge to be able to have the desired sensorgram that you want. Another problem that we could look into is all the other conditions that we know are able to unfold the tetrameric structure of streptavidin, like 8 molar guanidinium chloride solution. Or if you have very low ionic strength buffers. It's been reported that if you have very low ionic strength in your buffer system, the interaction between the streptavidin and the biotin at the binding site is very low. So you may run into ligand bleeding or leaching from your surface. I have always mentioned about being moderate with how much ligand we put on the surface. And I use this simplified diagram to explain. So let's say we have streptavidin, which is on the sensor surface, and we have excessive amount of biotin-lated ligand. And simplified on the right, I show you maybe because this part is going to be on the sensor surface, it's not going to be accessible to the biotin-lated ligand that's coming in. But there is equal propensity for the biotin to bind on this side or bind on that side. And because of the flexibility of the ligand molecule that is attached to the biotin, you could have an interaction between those two biotin-lated molecules on the surface of the streptavidin, and it could lead to multimerization. And as simplified in this diagram, this multimerization has occluded the surface of the binding pocket, and then it's preventing the incoming analyte from binding. And this will be the ideal situation whereby you have just monovalent streptavidin with one biting bind, and then the analyte just find its binding pocket and bind to it. So yes, excessive ligand is not very good in this situation because the binding itself is very rapid and tight. You don't need so much. And you could also run into this multimerization and also mass transfer effect, as we will see pretty soon. So overall, we say that the streptavidin sensors are very useful, just like the other sensors that we talk about. The ligands, even though we call it a capture coupling, is covalently coupled. So there wouldn't be any loss in ligand density during the course of your reaction, unlike the other chemistry that we have talked about, which may require us to re-immobilize some ligand onto the surface. The third thing that I would like to talk about is that the streptavidin itself could be used in a sandwich assay. Like we found out that if you have a carboxyl sensor that you are dealing with orientation issues, you could actually convert your carboxyl sensor into a sort of streptavidin sensor, which you could use to immobilize a bitylated ligand. Also, this can be also applied to NTA sensors. If you have an NTA sensor and then you decided that you are run out of a histag protein, or for some reason you have a bitylated ligand that you want to analyze on an NTA sensor, you could just immobilize a histag streptavidin onto the NTA sensor and then bring in your bitylated molecule. So this streptavidin is very versatile. Number 4 is that it's thermally stable, as we know from people who have had experience with the streptavidin. But like you saw in the sensorgrams that I showed you, improper handling or storing it at room temperature in buffer for a sensitive time could lead to a lot of NSB. And we should always be moderate with how much ligand we put on the surface, because we don't want to run into multimerization and surface heterogeneity and then mass transfer effect. Mass transfer effect has been highlighted here because I'm going to talk about it pretty soon. So here, let's assume that we looked at all these conditions and we successfully immobilized the ligand on the surface, no problem. But we are now moving on to the Analyte injection. Let's look at some of the problems that we could face during Analyte injection. So you have your bitylated ligand on the streptavidin sensor, as shown here. The next thing you would want to do is to inject your Analyte. And the normal thing in a good day, what we expect is that the Analyte finds the active site and bind to it. And then you have your beautiful sensorgram with little to no NSB. But then sometimes we happen to run into situations like this. Notice that the red curve is our channel 1 response, which is the reference channel where there isn't any bitylated ligand, so you shouldn't see any binding. But here we see these binding. So somehow the Analyte is binding to the sensor surface, or something is going on in the solution that we need to control. Then there will be need for optimization to be able to convert this sensorgram into something like this or better than this. And how do we do that? We optimize for NSB. Like I've been always mentioning, you could decrease NSB by doing reference matching the ligand density in both channels. On our system, we say that the ligand goes into channel 2. That is how channel 1 is our reference channel, because it's just like blanking your UV instrument. In the blank, there's not going to be any sample. So in that channel, there is no ligand going there. So after the ligand immobilization stop, you have a channel 2 which have the ligand, but then channel 1 there's no ligand. And then what you could do is that you are going to immobilize an inactive molecule. That in the case of streptavidin, it has to be biotin tag onto that channel, so that at the end you have two things. Two channels with basically the same densities, so that in doing so, for example, some of these molecules could be biotin, biotin-related BSA, and other biotin tag molecules. Remember that you could always biotin-late your stuff in your lab if you have the desired reagent. So always try to immobilize a control protein in channel 1. And then doing this, you are able to mimic the ligand density in channel 2 because you didn't put the ligand, the desired ligand, in channel 1. And then here we see that it's going to reduce the interaction between the streptavidin and then the incoming analyte, because you want the analyte to interact with the biotin-related ligand, not the streptavidin on the surface. So now that you have immobilized a control ligand, biotin-related ligand in channel 1, the streptavidin is not exposed anymore. So there wouldn't be any non-specific binding in that channel. Again, it's very important when you have very small, you are using small molecules in your SPR, because small molecule has a tendency to suffer from surface mismatch. So if you are able to match the densities in both channels, especially when you are dealing with small molecules, you wouldn't run into any sensitivity issues. So now let's move straight to mass transfer effect. Why you should be moderate with the amount of ligand you put on the surface. What happens when you have too much ligand? So mass transfer happens whereby the concentration of the analytes on the surface of the chip, sorry, my pointer is all over the place, is not equal to the concentration in the bulk solution. So there's going to be a deficiency of analyte on the sensor surface, as we see in the diagram below here. See, you have this gradient whereby there is a lot of analyte in your bulk solution, but then when we get closer to the sensor surface, there's a deficiency of analyte on the sensor surface. And when this happens, this is what you see in your sensorgram. It doesn't have the curvature of a normal sensorgram as we have seen in the past. So when you have a sensorgram that looks like this, it means your sensorgram is suffering from mass transport limitation. And how do you overcome this? To overcome the mass transport effect, number one, you could, because you have a gradient, a concentration gradient of the analytes between the bulk and then the sensor surface, you could increase the flow rate. Remember that flow rate should be moderate, just like how much ligand we always talk about. And you could set up the experiment in such a way that you have different flow rates. Let's say flow rate 1, flow rate 2, flow rate 3. And after you get your results, the kinetic parameters of the different flow rates shouldn't change. Then it means you don't have any mass transfer effect. But then if you have different flow rates giving you different Ka, then it means that some of your flow rates have an associated mass transport limitation to it. So choose the moderate flow rate that will eliminate the mass transfer effect or the mass transport limitation. Number 2 would be that you have to lower the ligand density. We saw that the ligand density, too much ligand could cause heterogeneity and crowding on the sensor surface. And also you could run into low RUs, but I will choose low RU as long as it's not in the noise region any day over like crowding and then inability for the analyte to bind to the sensor surface and multimerization. So choose a moderate amount of ligand to bind to your surface, and then you will be good. You would get decent sensorgram and you wouldn't have to deal with all these effects. And the third thing will be to use, let's say you are done with all your runs and you are not in the position to actually do all these controls. All hope is not lost, because in our processing software, which is the trace drawer, there is an option to correct for this mass transport effect. It's called the diffusion control model, as shown in 3 here, and it's going to correct for this mass transport effect. So you could run into mass transport effect. limitations, but then you have all these three things to troubleshoot them. Now let's go straight into the hydrophobic coupling. For the hydrophobic coupling, like I mentioned, we have two types of sensors. We have our liposome sensor. As their name implies, it will be used to immobilize liposomes on the surface. So it has a lipophilic molecules on the surface, which will be used to immobilize intact liposomes, as illustrated in the figure below. On the right is our general purpose hydrophobic sensors, whereby hydrophobic ligand would form a monolayer of ligand on the surface of the sensor, as shown here. So depending on the system that you are studying, you could choose between a liposome sensor or a hydrophobic sensor. How are we going to be successful on these two? Because they are both hydrophobic, I'm going to treat them like the same. Like what applies for liposome will be basically applied for, unless you have specific system that requires different conditions. So let's say if you have your liposome or hydrophobic sensor, that you would want to immobilize your hydrophobic ligand onto it and then do your analysis. First of all, you would have to clean the sensor surface. Unlike other sensors whereby maybe one injection of the cleaning agent will get you to a stable baseline, we find out that for these systems, because they are very reactive, you may need to inject several times of the detergent, which could be chaps or octyl glucopyranoside onto the surface, and you are going to keep injecting maybe up to like 3 times before you get a stable baseline. You are not going to stop injecting until a stable baseline is reached. Let's say you put these detergents onto the surface, and then you happen that it looks like the detergent is kind of like there's excess amount of detergent on the surface. You want to be able to remove it because your ligand is going to come onto the surface to bind. So you can do that by injecting about 30% ethanol if you need to remove the excess detergent on the surface. Then the ligand will be immobilized into channel 2 as usual. The next thing is to immobilize a control hydrophobic molecule into channel 1, similar to what we saw with Streptavidin and other chemistries. Mimicking the ligand density will reduce a lot of NSP and also prevent the sticky hydrophobic group from interacting with your analyte. Number 4 will be that after you have immobilized the ligand and then the control, you may not be having a stable baseline, because we need a stable baseline to work with. What you could do is to inject some sodium hydroxide onto the surface, 10 to 20 millimolar sodium hydroxide, and hopefully you'll be able to stabilize the ligand before you do the surface before you do your analyte injections. 5 is if you want to know like you have had enough ligand on the surface, what you could do is that you could do a saturation test with BSA. So injecting a 0.1 milligram of BSA onto the surface would show you whether you need to put more ligand or not. When you see that the injection of BSA result in a very high response, but then it's going to come down because it's not going to bind, but then the RUs increase very high, it means that there's more capacity on the sensor surface to bind. The sensor has this capacity to bind more ligand. So you are going to go back and inject more hydrophobic ligand onto the surface. But then when the BSA injection doesn't result in any significant increase in RU, then you are okay. You may have enough, sufficient ligand on the surface, because you don't also want to overcrowd the surface. Okay, so what about the things? Now we know the things that would make us successful. What about the things that we need to avoid? Detergents. We need detergents to condition or clean the surface. But then after the ligand immobilization, we don't need any detergents. It's just like when you are dealing with NTA sensor and then you don't want excess imidazole in your buffer. You don't want detergent that is going to outcompete your hydrophobic ligand on the surface. Another thing is that we have advised that if you are coming back to your instrument or your ligand the next day, you could leave the instrument in standby with a chip and the ligand on the surface and then keep flowing buffer on it. But then we find out that these liposomes here don't have a very long half-life. So what happens is that you may have to strip your ligand. The good thing is that you can strip it and then put a fresh ligand on the sensor surface. It's not covalent, so don't worry. Before you go home, it's advisable to get reproducible data. Maybe some of the liposomes are very stable, but what I would advise is that after the day has ended, you could strip off your ligand from the surface and then come back again tomorrow, reimmobilize it, and then you could do the Analyte injection again to get a more reproducible results. And also, because it's going to be hydrophobic interaction, you don't need so much salt. Remember, some of you who have done like studies on, let's say, micelles, we know that effect of ionic strength of micelle because sometimes it changes the hydrodynamic radii of the micelles. So if you want to have a uniform system and you also want to drive that hydrophobic interaction, put physiological amount of salt in the buffer, but don't go too high. We also advise to work with buffer system that has been degassed and then filtered because these particulate and air bubbles could also disrupt your liposome or your hydrophobic moieties from the surface. So at this point, we know that we could have success on these hydrophobic sensors as well by following the conditions that we discussed in the previous slide, and then also avoiding these conditions. And then that would bring us to the summary. So in summary, I would say that NSB, which is what we all don't want, unfortunately exists in all these kind of technique. But then we discovered that we could always overcome it by using control molecules in channel 1, which is called reference matching, or buffer optimization, regulating how much salt you put in, or removing detergent in terms of if we are dealing with the hydrophobic molecules from the surface. Also, we would also want to take care of how we handle our sensors because as we saw, the streptavidin in our case, we saw a lot of NSB when it was left at room temperature for extended time. And also look at the sensor's properties such as whether it has expired or not, because it could also give rise to a lot of NSB. And the last thing I would like to mention is bulk effect. Let's say you get your Analyte stock from a solution that has DMS, so especially when you have a small molecule work, like your Analyte is a small molecule and it's solubilized in DMS. So before you are going to dissolve it in your Analyte buffer, but then you have to match the amount of the final concentration of the DMS, so in your Analyte that you are going to inject to what is in your run buffer. So you are going to add DMSO to your run buffer to prevent this mismatch, which will eliminate this pattern of response from your sensogram. So after you have overcome NSB and bulk shift, you should be left with this part of the equation that says that response that you are getting on your sensogram is totally specific binding, which is good but then it happens that sometimes you don't see any response or your response look weird. What could be happening is that you could be having air issues, and then you may have to go back and recollect your reference spectra or degas your buffer, or it's something to do with how you collected the reference, which I have talked about it in details in webinar number, I believe 4. So you could look at the details on that, how to do that, or just email us and then chat with us too. And also, when you inject buffer, because we encourage you to inject buffer to see that whether the response that you are seeing is coming from your buffer or something else, buffer injection shouldn't give you any peak. If you begin to see peaks or a lot of drift or weird sensogram, and you have done all the right things at the top here, maybe it's time for you to clean your instrument. I present to you the picture on the right because I like to look at the instrument like the plates that we eat on. After we have our dinner, we always want to clean the plates that we eat on, right? Let's say you have a piece of steak, excuse my pronunciation, and then after eating, you have grease on the surface. What you do is that you use this agent here and then clean the plate and then put it away or stick it in the dishwasher and wash it later. So look at your instrument like your plate. If you do a run and the buffer has salt. Let's look at the salt, like the grease on the plate. If you had left the grease on the plate on the counter, what would happen is that it's going to solidify, and then it will become a place for bacteria to grow, and you will end up with a lot of colony and mold and what have you on your plate, and nobody wants to see that because it's not nice. Why would you want your instrument to be treated like that? Treat your instrument the same way you would use this agent to clean your plate. Rinse the injection pot after the run to prevent salt precipitation. After each run, just inject a couple of runs of water to remove the salts from precipitating into your buffer line. Weekly or bi-weekly, you could do a basic cleaning. We have talked about this cleaning because we find out that sometimes, personally, I've done runs whereby I think there was a lot of NSB, but I've done all the things to my buffer that is going to control NSB. And then there's still NSB, which is like ridiculous. So I go back and clean the instrument, and tada, all the so-called NSB wasn't really NSB. It was just contamination from the fluidic lines. So cleaning is very important. Also, when you are ready to shut down your instrument, make sure you do a full instrument clean to clean the back of your pumps and things like that. I always also want to think about the instrument. Look at it like your HPLC. Think about why we put sodium azide in HPLC water. Like if you're cleaning the water that's connected to the instrument, usually put some very low percentage of sodium azide to actually kill anything that will grow on the column. The same way, for us, we don't have columns, but we have fluidic lines. So cleaning will be very important. So that brings me to basically my last but one slide. That is a question that we get a lot. Are your sensors reusable? The answer is yes and no. And I'm going to take each sensor and talk about it briefly. Starting with the carboxyl and the imine, I'm treating them together because we know that the coupling procedure is covalent. If you have the sensor that has the ligand bound, you will not be able to remove the ligand and then put it back like you would do for the hydrophobic or the NTA sensors. What we would suggest you to do is that keep the ligand on the sensor chip in the instrument and keep the buffer running on it, and come back the next day and do your Analyte injection. But before you do several Analyte injections, we encourage you to repeat a previously run concentration to make sure everything is okay, and then you proceed. But what conditions are we supposed to avoid? So this actually summarizes what we have discussed in previous lecture. We know that we don't want to have a primary imine in our buffer when we are immobilizing a ligand onto the carboxyl sensor, because it relies on a primary imine from our ligand. So let's say you want to control a non-specific binding. So you decided that I'm going to add some BSA to my buffer. BSA is a protein and it's going to have primary amine. So if the protein, the ligand is flowing in a buffer that contains BSA, then it means that BSA has the chance to also couple to the sensor surface. And the same thing is with azide, as we see here. And the second thing I would want us to avoid is old solutions of NHS EDS, especially EDC. EDC is hygroscopic. It has a short life, shelf life. So we would want to keep it away from water, from solution for extended time. So I would say that make your solution of EDC NHS fresh, and then combine it just when you are about to inject it into your onto your sensor surface, so that you don't run into like unsuccessful activation of your carboxyls on the surface. And if you are doing ligand immobilization on this carboxyl sensor, you would want to have it at low ionic strength, because you would want the ligand to be positively charged in order to enhance electrostatic interaction between the negative group and the positive sensor. So if you have a stock of ligand that is in very high concentration of salt, what would happen is that you see a bulk shift pattern. The ligand never binds, it just falls off the sensor surface. Now let's look at the NTA sensors. The NTA sensor, as we discussed, that yes, you could strip the surface of the ligand and then bring it back and immobilize, and then re-immobilize the ligand back onto the surface. all what you need to have is acidic condition, as we see HCl solution, very high concentration of imidazole. So anything that is going to break that coordination complex, that is what is going to strip off the ligand. And you could also immobilize it by using these steps. The steps are also in the tech guide that accompanies the sensor chip whenever you buy them. So to be successful on the NTA sensor, you would want to avoid all the conditions that will strip your ligand from the surface. Acidic pH, divalent chelators like EDTA, and then high concentration of imidazole. And now streptavidin and biotin sensors. Even though we call them capture coupling, that like we spoke about briefly, it's still gonna like covalently coupled. The ligand will be covalently coupled, like, because you cannot separate it from the sensor surface. So it means that you will not be able to kind of like take the re-immobilize the ligand again. But then we find out to be successful, you would have to handle your streptavidin with care. Put it in the fridge when it's in solution, and also avoid all the conditions that will destabilize the tetrameric structure of streptavidin. And now let's look at our two last sensors that we talk about today, the liposome and then the hydrophobic sensors. Similar to the NTA sensors, you could strip the hydrophobic ligand from the surface and then re-immobilize it. All you need is a detergent that is going to outcompete your hydrophobic ligand on the surface. And then you are going to re-immobilize it when you come back with the protocol that we give you. And then to be very successful on this, you would have to, after the ligand is on the surface, to prevent it from bleeding from the surface, you don't have to put any detergent. You have to be moderate with the amount of salt you use. And then, because the half-life of these liposomes that is going to be on the surface, it's a couple of hours, a few hours. You don't want to leave it there for so long. Strip it, come back, re-immobilize it, and move on for there. And then the gas will always filter your buffers. The same thing applies for the hydrophobic sensors. With that, I would say that Nicoya has a lot of useful sensors. And all these sensors have their individual personalities, just like me and you. We have our pros and cons. Some are very versatile, and then they are very customizable, like we saw the sandwich assays. The choice is in your hands. Is what you have in your lab, the system that you want to study, and what you can do. Like, could you bitinylate your ligand, or you could just purchase it? It's up to you, and we have all the different chemistries that you may need for a successful SPR study. And I also want to indicate that you may run into unusual sensorgram problem, but then we find out that for every sensor, there's always going to be a way to overcome it, like optimizing your buffer condition, your samples, and then even how you collect your reference, and cleaning. Maintenance is key here. With this, I would say thank you, and then I will welcome your questions. And if I didn't cover something that you would really want to know about, feel free to type it in or just email us at our support on our support portal. Are there any questions? Is there anything that needs clarification? So thank you again. And then I would gladly elaborate on any part of the slide that need explanation or any questions that you may have. Okay. Are there any questions? Take your time. I'm going to go through any part of the slide that you want me to go back to, and then we talk. Okay, let's give it a minute or two, and if there are no questions right now, feel free to contact us if questions arises or there's any part of the presentation that wasn't clear, and we will be glad to address it. So with this, I would say again, thank you for making time for this webinar, and we will be back shortly with another episode. Bye for now.